Hi everybody, and welcome to the video for chapter 5.2. This section's it's titled the second derivative. So we're going to learn about this second derivative, but the idea of the section is that we're going to continue analyzing functions, and we're going to see how the second derivative helps us predict the shape of those functions and the behavior of those functions. So there's four parts. Four parts. There's two part fours, but that's okay. Part one, I'm just gonna identify what the second derivative is. In part two, we'll look at concavity and how it relates to the second derivative, and I'll define what we call inflection points. And then we'll do some examples, and I will then introduce you to the second derivative test. So let's start our discussion with actually what the second derivative is. So remember, the first derivative, we call that f prime of a function. That measures the rate at which the function changes. So our first derivative measures the rate at which the original function changes. And that's represented by the slope of the tangent line. The second derivative, we call this f double primes. There's two little primes there. This actually measures the rate at which the first derivative changes. So it's 1 degree of separation, essentially. And here's our formal definition. Given a function f of x, the second derivative, and we denote that by f double prime, is the derivative of the first derivative. So it measures the rate at which the first derivative changes. We can take this notation one step further, and we can say, all right, we're going to take a derivative of the first derivative, but the first derivative is obviously the derivative of the function. So when you're taking a second derivative, it's two steps. You first do the first derivative, and then you take a derivative of the result, and that gets you your second. Now, there's some notation for this, and that's kind of the difficult part. If you have a function y equals f of x, we can identify the second derivative in a couple different ways. The first way, and the way that we'll use it most, is f double prime of x. You could also see just y double prime. And you could also see this notation d squared y over dx squared. What this says is that you're taking a second derivative of y with respect to x. And that notation is a condensed form of what we see here, where you actually have two x's on the bottom, and on the inside you'll have the function, and that's a condensed way to write the second derivative. But in any case, we're going to care mainly about this notation here. So what we can now do is a few examples. So I'm going to zoom up here, and essentially we can find some second derivatives. And it's pretty straightforward. You just need to do two steps. So you take your function, and you're first going to find one derivative. So use your power rules. Then once you have that first derivative, you can find the second derivative, again using power rules, by just taking the derivative of that derivative. Similar for part B, we're given a function y. I am going to rewrite the function y as 2x to the 1/2 minus 3 ln of x. And if you want to find, we're looking for the second derivative of y with respect to x, that's the same as y double prime. So if I first find y prime, that's your dy dx, and you take a derivative. So I'm going to use the power rules and my logarithmic rules. And you'll see that you end up with, on the right here, you'll end up with x to the minus 1/2 minus 3 over x, which is really 3x to the minus 1. And then we're going to go again, we're going to take y double prime, that's the second derivative of y with respect to x. And you're essentially, all you're doing is taking another derivative of this function. So we're going to use the power rule again. So bring that minus 1/2 down, take 1 away from the power, then do the same thing. You'll bring the minus 1 down, take 1 away from the power, and then we just clean this up. So we have actually plus 3 over x squared. And there's your second derivative. So it's just practicing derivatives, but you have to do it twice. Part C here is a little more involved, because to find f prime, we do need the quotient rule. And so once we identify that we do need the quotient rule, you have to spend a minute there using the form of your quotient rule to get your derivative. So I've written that workout here. You can pause and kind of check out those steps. But in the past, I've told you not to simplify. But when we're taking a second derivative, because we're going to need to go again, I do recommend going through these simplification steps to make it as simple as possible, because now I have to do f double prime again, and you're going to need to use the quotient rule one more time. And the quotient rule will be on the rightmost expression that we have here. And in this case, we don't need to simplify any further because that's our final second derivative, and we can just circle that, and that's our final answer. Now, the thing I do want to highlight is look at this term here. I want to make sure that you guys see what's going on with this term right here. This is the derivative of the denominator. So that's part of the quotient rule, and that's actually a chain rule that's needed for that part. All right, because you're taking the derivative of 4 minus 2x squared. So your u is 4 minus 2x, and your derivative of u is minus 2. So when you take the derivative of this whole thing, you're going to get 2 times 4 minus 2x to the first, all multiplied by minus 2. And good thing I'm describing this, because I did forget that minus 2 there. There will be a minus 2 multiplied by that expression. All right, and that is your chain rule. So be careful, because sometimes you'll have chain rules kind of sneaking in there. So now that we know how to find second derivatives, let's see what it actually means, what it does for us. And you'll remember in an earlier section this year, you've learned about concavity. Now, concavity tells us about the shape of a graph. And we have two cases, either concave up or concave down. Concave up, and I always use this analogy, it's like a cup. So concave up, the graph will resemble a cup. So it'll either look like that, or it might look like this, or it might be both of them combined, but it'll have a shape like a cup. Concave down is like a frown, so it's going to have a downward shape like a frown, and it'll have the curvature given by one of these two graphs. Okay? How does this relate to the second derivative? Well, let's highlight exactly what's happening with the slopes on these graphs. So with my blue marker here on these graphs, I'm gonna draw some slopes. So imagine little tangent lines that I'm drawing, and these tangent lines have slopes. And clearly the slope's changing. Okay, and these slopes are indicative of the first derivative. Notice that the slopes, they start off pretty negative. All right, then they start leveling out, and then they start getting positive, and then start getting really big. So my slopes are increasing. Well, that means that your first derivatives are increasing, because the first derivatives tell you about those slopes. All right, but remember, the second derivative tells us about how the first derivative is changing. And since the first derivative is getting bigger, that means my second derivative must be positive. And this is what I really want to highlight. Whenever you have a concave up graph, your second derivative will be positive. Now we can say the same exact thing, exact same arguments over here. Let's get a different color. I'll use green. And you highlight your slopes, right? These are your little slopes, and they start off pretty positive, and then they start to level off, right? And then they start getting negative. So your slopes are actually decreasing, which means your first derivatives are decreasing. All right, and again, the second derivative tells us how the first derivative is changing, so in this case, the second derivative will be negative. So when you have a concave down function, that means you have a negative second derivative, and that's the important thing that I want to highlight here. Now, on a graph, think of a roller coaster graph of, a nice polynomial. You've got this polynomial that kind of is like a cup, then it's like a frown, and then it's like a cup, and then it's like a frown, and it can kind of keep going like that. There's these special points where it changes from being a cup to a frown, and from a frown to a cup, and from a cup to a frown, and there's these changes where the curvature is changing on a graph. These ordered pairs, so if you highlighted these ordered pairs, those have a special name. That's where the concavity changes, and we call those points of inflection. Those are the ordered pairs. They're ordered pairs on the graph where the function, first of all, must be defined. So we don't want, it needs to be in the domain. We don't want holes and asymptotes and things. And the concavity of f changes. So it goes from concave up to concave down. Now, finding these points of inflection, they can occur at x values where the second derivative is 0, because that's generally where it's going to change from being positive to negative. So you'll have a concavity change. but they may also occur when the second derivative doesn't exist. So essentially, our job is going to be to find these POIs. I'm going to call them POIs from now on. And these are potential POIs. So first of all, we have to be able to find where the potential POIs are, and then determine if there actually is a change of concavity. Now there's 4 cases for points of inflection. I'm going to draw those 4 on the right here, and then I'll comment on them. So I've drawn the 4 situations, and I've highlighted the point of inflection on the graph. So here we have concave up, and then it changes to concave down. So that's a change of inflection. Here we have concave down, and it changes to concave up. Here we have concave up, it's part of a cup, and then it changes to concave down, part of a frown. Notice you don't have to have the whole cup. It just needs to be part of a cup. You don't have to have the whole frown, just part of a frown. Then over here you have the frown, and then it changes to being a cup. And those are the 4 situations we're gonna see. All right. On the next slide, we'll talk more about what all this means. So our main goal here is to be able to determine the locations, so the x coordinates of all your points of inflection on a given graph. And then we want to find also intervals for which your function is concave up, like a cup, or concave down, like a frown. So basically, we're trying to determine what the function looks like and where special things are happening with that curvature. And so just like the last video, I've broken this into 4 parts, 4 types of questions you're going to see based on what information you're given. But the directions for each question is always going to be the same. Find the x coordinates of all POIs, and find intervals on which the function is concave up and concave down. So we're going to see this 4 times. Type 1, the first example you'll see is when you're given the graph of f of x. This is the easiest type because it's all right in front of us, and we can actually target what's happening here. Now, first of all, let's try to find those POIs. The graphs, generally on WebAssign when you're doing homework, it'll be very, very clear where the change is happening. But I'm going to go with my blue marker, and I'm going to say, okay, I'm going to start on the left. I'm on a cup. I'm part of a cup here. All right, and then it seems like my cup is ending, and I'm turning into a frown. All right, so here's my frown. And then it seems like my frown is ending somewhere around there, and I turn into a cup. All right, so that's the 3 different changes. So I do have a change right here, and I do have a change kind of right around here. Now, again, it's kind of arbitrary. So you might say, Dave, why are you putting it there and not at 8 and whatever? But to me, it looks like that's where the change is happening, and obviously it'll be more clear with an actual drawn-out graph. So the locations of my POIs, based on the graph that I've drawn here, would be x equal to 4 and x equal to 8.5. So 17/2. I like fractions. And then the intervals on concave up and the intervals on concave down, I'll draw those next. And all I'm doing here is I'm saying, okay, yep, it's concave up from -infinity up to here, from here all the way to infinity, and it's concave down in the middle here. And you express those as intervals as we've done all semester. That's type 1. Those are generally the easier ones to picture. Now type 2, let's do the same example. X coordinates of POIs, intervals for concave up and intervals for concave down. I'm giving you a graph, but I'm giving you a graph of the second derivative. So that's a big warning sign. I didn't want to write that. That's a big warning sign right here. Really, really important. So let's look for the POIs. Now, the POIs occur when the concavity changes. But we can't look at this graph and try to determine what the concavity is, because the shape of this graph doesn't tell us anything about the shape of the original graph, f of x. So don't look at the shape of this and try to look for cups and frowns. So the first thing we need to do, here's our solution. The first thing we need to do is draw a number line. So this is going to be step 1. I'm going to draw a number line just under this graph. And on the number line, I am going to label all of my potential points of inflection. And as I stated on 2 slides ago, your potential POIs occur when your second derivative is 0 or when the second derivative does not exist. And guess what? We're looking at the graph of the second derivative. So that's awesome. We have that it's 0 at 0, so there's one potential POI. I have that it's 0 at 4, at 8, and at 12. So that's when my second derivative is 0. And those are all of my potential points of inflection. Okay. Now let me zoom up here. The next thing you're going to need to do is on either side, so this divides our interval up, our real axis up into 5 intervals. And what you need to do is on each interval, tell me if it's concave up or concave down. So I'm going to look up here from minus infinity to 0. Are we concave up or concave down? So a lot of you will say, oh, we're concave up because it looks like we're part of a cup. That is, it is concave up, but it's not because of the shape. It's because the second derivative is positive. So those values are above the x-axis. So that means we are concave up. All right. Now from 0 to 4, it looks again like we're concave up, but we're not. We're actually concave down because this is the graph of f double prime, and these values, the y values here, the f double prime values, are negative. So as soon as you know that your second derivative on this interval is negative, then I know that this is actually concave down. All right. Same thing from 4 to 8, you have positive values, so positive second derivative. So that is concave up. So again, it looks like it's down, so don't worry about what it looks like on that graph. It's where the y values are. Then on this graph, on this side, we have f double x, a double prime of x less than 0, so this is concave down. And to the right of 12, f double prime is positive. They're positive y values, and that's going to be concave up. Okay, so notice that you get a change of concavity at all of these points. These are my potential points of inflection, but I can now actually say that those are all points of inflection because there's a change of concavity happening at each and every one of them. And the last step is to express the intervals on which it's concave up and concave down, and I'm just basically condensing what I've described here to those intervals, and then same for the concave down. I really want to highlight this, guys. This is going to be on an exam, and so many people are going to get this incorrect in terms of looking at the actual shape. The reason why we know this is concave up from minus infinity to 0 is because these values are positive. They're above the x-axis. It's concave down here because these values are negative. They're below the x-axis. And that's only because the graph that we're looking at is f double prime. So it matters what the graph is that we're looking at. Type 3, again, same exact problem, but in this type of problem, I'm going to give you the function f of x. All right. Now, there's a particular procedure we're going to follow, so I'm going to outline those steps. We want to find the POIs, and we want to find intervals for concave up, concave down. Step 1 is going to be to compute the first and second derivatives. I can't stress enough how important it is to be able to do these basic derivatives quickly and efficiently, because if you get those wrong, it makes the whole rest of the problem really, really difficult, and so that's very important. That's step 1, so I'll write 1 for that. Step 2, you're going to highlight your potential points of inflection. And to find those potential POIs, you look at your second derivative and you try to see if it's ever does not exist, which it doesn't in this case. But then you try to set it equal to 0 and see for which x values your second derivative is 0. And that's going to involve factoring. So I'm going to factor a 12x out of both terms. And you're going to find that you get 2 points, x equals 0 and x equal to minus 2. Those are potential POIs. All right, so we've got these potential places where I could have a concavity change. And actually, I'm going to put the factored version of f double prime right up here because we're going to need it in a moment. So the third step, now once you find those potential points of inflection, you're going to take those and you're going to put them on a number line. So in this case, we have minus 2 and 0. Now on that number line, so let me zoom up here, on that number line, that's going to divide our graph into 3 intervals, separated by those potential POIs, and on each interval you're going to pick a test point. So pick, oh, that's not on the interval, pick something that's in that interval. So here I'm going to pick -1, you have -3 over there, and then x equals 1. And finally, you're going to actually evaluate the second derivative at that point to see if it's positive or negative. And I'm going to use the factored version of f double prime here. So when you use the factored version, you put in -3, you're going to get -36 times -1, and that's a positive number. So this is concave up. All right. Then we're going to put in -1. So if you take f prime and you put in -1, you're going to see that that is negative 12 times 1, which is negative. So this is concave down. Then you take, that was an f double prime. Then you take f double prime evaluated at 1, you'll get 12 times 3. Again, I'm using the factored version of f double prime. It's a lot easier to work with. And this clearly is positive. So that's concave up. All right. So we're concave up on the left of -2, concave down, and then concave up again. So notice there is a change that happens at -2 because it goes from concave up to concave down, and there is a change that happens at 0. So these are both going to be actual POIs. And then I can finally express my intervals for concave up and concave down. And there you have it. There are all of our answers for what we're actually looking for. And again, this gives us a sense of what f of x, the original graph of f of x, is going to look like. We do have the function for f of x, so I could go off to the side and I could graph f of x. And I do encourage you guys to do this. Graph it and make sure that what I've written here seems to agree with what you see graphically. And finally, last but not least, type 4. In this example, we're going to be given actually the second derivative as a function. And we'll be asked to find the same exact thing that we were asked to find previously. So let me put a big warning sign there. It's really important that we know exactly what we're working with here. So as a solution, we're going to do the same thing, but we don't have to find the second derivative because we're given it. So we're going to jump right into that same method by finding the potential POIs. Okay. Now the potential POIs, remember, they occur when either f double prime of x is 0 or when f double prime of x does not exist. And in this example, we have some of each of these types. So when f double prime does not exist, that's at x equal to 4, because then our denominator will be 0. So that's one of our potential POIs. When f double prime equals 0, that's when the numerator is equal to 0. Okay, so the only time that the second derivative will be 0 is when the numerator is 0. So you're going to set that numerator equal to 0 and solve for x. So x is either 1 or x is -2. Okay, now these points, 1 and -2, and as well as 4, we're going to take these potential POIs and we are going to input them onto our number line. So we have -2, we have 1, and we have 4. That divides our number line into actually 4 regions. You choose a test point from each of these regions. Choose something nice from those intervals. So these are the ones I'm going to use. And then I'm going to input that to the second derivative. Okay. Now you can do this out fully and find exactly what the number is, determine if it's positive or negative. But actually what I like to do is just play a little positive plus or minus game. So if we take -3, right, I'm going to throw it into this second derivative right up here. When I put -3, the first factor, -3 minus 1, that's going to be negative. Then -3 plus 2 is negative. And then I have -3 minus 4 is negative raised to the 5th. And again, you can just find the numbers. That's perfectly fine. But notice this is going to be a negative times a negative over a negative, because any negative raised to an odd power is negative. All right, and a negative raised to an even power is positive. So that's kind of how you can play this game. So that being said, I have 3 negatives, and when you have 3 negatives, you'll end up with a negative. So f double prime is less than 0 in this case, and therefore on this interval you are concave down. All right, we can do the same thing for f double prime at 0. You're going to get a negative from the first factor, a positive from the second factor, and then a negative to the 5th power. So after all is said and done, this will be a negative times a positive over a negative, and that's going to end up being positive. All right, so f double prime of x would be positive. And I'm going to skip ahead. I'm going to do the same thing for the other two intervals, and we'll see what we get. And what we ultimately end up seeing is that we have concave down, then concave up, then concave down, then concave up. So all of those points are POIs. Every point that I have, all my potentials, x equals -2, 1, and 4, are all POIs, and then I can find my intervals. And that completes this last example. So please practice this. You'll see all 4 of these types on your WebAssign. The last part of the lecture, we're actually going to learn what we call the second derivative test. So think of this as similar to the first derivative test. It'll help us determine when I have relative extrema. And here's how. So if you knew that you had a critical point, so remember a critical point on a graph is when you have a derivative that's 0, so it's at your peaks and your valleys. If you had a critical point and you knew that that critical point was at the bottom of a cup, and the cup is when the second derivative is positive, well then you know that it has to be a minimum. All right. If you knew that you had a critical point and it was at the top of a frown, when the second derivative is negative, well then you know you need to have a max at that point, because it'd be the top of a peak. And that's the idea of the second derivative test. So what we do is we find all of our critical points. These are my critical values. And then we evaluate the second derivative at that critical value. If it's positive, then we have a min. If it's negative, then we have a max. All right, so let me zoom down and show you that explicitly written out. So our second derivative test says if a function is defined on an interval and you have a critical point, that's all that this is saying, then for a positive second derivative, you have a minima, and for a negative second derivative, you have a maxima, all right, a relative max. And if the second derivative is 0, this test is actually said to be inconclusive, okay? Let me zoom up and we'll practice this. Oh, I actually have it on the next slide. We're going to see how this actually works in practice. So here's a real quick example of using the second derivative test. Suppose that your function is continuous, so there's no points of discontinuity. We're going to determine if each point below is a max or a min, or possibly neither. And there's also a situation where we might not have enough information. Okay, so let's go through. Let's see how this works. Part A. They're giving me a point. So there's on some mystical graph, which I don't have here. So I have some point. This is my ordered pair. This tells me that -4 is a critical value. So it is a point where I could have a max or a min. And this tells me that I am concave down. So I always draw a frown, and I know I have a critical value. So at that point, you will have a max. You'll have a relative max. All right, and that would be the answer. Yes, we have a relative max. It's a critical value where I have a second derivative that's negative. In the next example, I have an ordered pair. My first derivative is 0, so 0 is a critical value. And my second derivative is 0. And this means that the test, if you look back on the last slide, the test here is inconclusive. So that means I don't have enough information to determine what's actually happening. It doesn't mean that it can't be a max or a min, it just means it's not conclusive. And finally, the last example, I have an ordered pair. My first derivative is 0, so 3 is a critical value. All right, and then I have concave up. So if you ever forget, the second derivative test, just draw a little picture. It's concave up, right? So let me do that in black. It's concave up, and there's your critical value. And therefore it must, in this case, it'll be a min. So it'll be a relative min. And we'll finish off this video with one last example of the second derivative test. Suppose that you were asked to use the second derivative test to find all relative extrema. Well, there's going to be a couple steps here. Step 1 is to find all critical values. Well, that involves finding the first derivative. All right, so actually when we start, we should find the first derivative and we should find the second derivative, because I know I'm going to need both of those things eventually. So you use your power rules. and you'll get these two derivatives. So for the critical values, you're going to take your first derivative, and you are going to determine when this is equal to 0, because that's when I have my critical values. Or when the derivative is undefined, but it won't be in this case. So you just need to do a little math, factor out your -3, and then solve for x. All right, the next step is now we're going to actually apply the second derivative test. So we're going to evaluate f double prime at those critical values. And so I'm using my second derivative, I put those numbers in, and you're going to get a number, and it's either positive or negative or possibly 0. Now, since in the first case it's negative, so that's concave down like a frown. So I always draw the frown, and then I realize, yep, at -3, at x equals 3, we have a relative maximum, okay? Because that's the second derivative test. The next one is up like a cup, so it's actually a minimum. It's a minimum point. At x equal -1, we have a relative min. And that's how quick and easy the second derivative test is to find the locations of your relative extrema. So that's it, guys, for this section. Please practice it. Hopefully you get to see the utility of the second derivative and how it helps us determine a lot about the shape and the curvature of these graphs. In the next section, we're going to put all that together and actually start to look kind of at the extreme sides. All right, that's it, guys, for chapter 5.2. Practice this. Hopefully you got to see the utility of the second derivative, and you can see how it helps us determine stuff about these functions and about the shapes of these functions. In chapter 5.3, we're going to learn one more step, and then we can put it all together and be able to get a full picture of what these graphs are doing and how that affects us in the real world.